My name is Timo Groß and I'm happy to present Deep Statistical Model Checking. This is joint work with Holger Hermanns, Jörg Hoffmann, Michaela Klauk and Marcel Steinmetz. With our work, we made the first step towards combining the power of neural networks and the model checking techniques of verification. In particular, we want to analyze and verify the behavior of neural networks. This desire arises naturally due to the complexity of neural networks. We demonstrate that deep statistical model checking is a lightweight approach to check the behavior of neural network systems. We have two goals. Firstly, quality assurance. We want to know how high the neural network induced safety risk is and how good the neural network is compared to the optimal policy. Secondly, we want to give feedback to the design process and answer the question whether further training improves the neural network and which parts of the system have to be trained further. To achieve our goal, we could in principle start with a naive approach. First, we look into the neural network and try to do the verification there. But the neural network structure is extremely complex and this analysis strategy will explode. Second, we could use standard exhaustive model checking for verification. But there we would run into the state space explosion problem. We implement our approach in modes, the statistical model checking tool of the models toolset. We use the input language Jani, which is a model interchange format supported by many model checkers. Exhaustive probabilistic model checking is limited by the state space explosion problem. In statistical model checking, sampling techniques are used to check a given formal specification. In the presence of non-determinism, quantities of interest are defined with respect to schedulers that resolve all non-deterministic choices. So far, nodes had the option to uniformly resolve non-determinism. We implemented a new option called Oracle. This option serves as a black box resolving non-determinism. We here concentrate on neural networks. We therefore also implemented a neural network evaluation support in modes to be able to forward the input directly through the learned neural network in modes. The return is an action applicable in this state, which gives us a decision on how to resolve the non-determinism, such that we can argue about a Markov chain in the simulation engine. We call this whole method deep statistical model checking. The technique is useful to assert the neural network's behavior. Usually, the objectives for neural network learning are not identical to properties checked in the model checking context. But for moderate-sized models, it is possible to quantitatively compare the neural network action policy with the optimal policy for the same goal. In summary, deep statistical model checking is a lightweight approach to verify the transition behavior of neural network action policies because it merely requires to call the neural network on sample inputs and thereby circumvents the state space explosion problem. We evaluated the performance of our approach in a case study on racetrack models. In principle, Racetrack is a pen and paper game you can play on a square sheet of paper. The track consists of a start line, call it in red, and a finish line, call it in green. Further, there are walls the car is neither allowed to touch nor to drive through. The goal is to reach the goal line as fast as possible. The game can be seen as a very simple autonomous driving application, and the whole process can be modeled as a network of MDPs in Jani. Racetrack has already been used as a benchmark in a variety of works on AI autonomous decision making. The car can accelerate by -1, 0 or 1 in x and y dimension, which gives us 9 possible acceleration actions at each position. We start with a speed of 0 in both directions. Afterwards, the speed is calculated by adding the chosen acceleration every time a new action is taken. To make the game more exciting, the setting cannot only be deterministic, which means that the action always have to decide outcome, but we can also add noise to the track, which means that the action may fail with a certain probability, as the car engine fails and it continues driving with the previous velocity. In our case study, we evaluate the car controller given by the neural network based on the probability that the car reaches the goal without crashing. We did our experiments on 3 different maps with increasing size. Before we take a look into the overall evaluation of deep statistical model checking, let's have a short glimpse on how to train the action policies. A state-of-the-art deep Q-learning approach is used where an agent whose behavior is represented by the neural network policy is trained iteratively. In each round, the game is played with the current policy and afterwards, the weights of the neural network are adapted according to the obtained reward. When learning policies for Racetrack, we evaluated 2 strategies which differ in the starting points of the sample games in deep Q learning. Either we can only train the neural network by starting from the start line, or we can allow to start randomly anywhere on the map during the learning procedure. This makes a big difference because when starting randomly anywhere, the goal is found earlier as soon as a state close to the goal is chosen. The neural network we used for reinforcement learning consists of an input layer with 15 nodes. The inputs are the current state information, which means the current position of the car, the velocity, as well as wall and goal distances. In the middle, we used two hidden layers with 64 nodes each and an output layer with 9 nodes, one for each possible action. We see the neural network is not that deep, but it has 4 layers, which is sufficient to learn good policies in Racetrack. As the last step, we are now able to evaluate the learned policies with the statistical model checker modes. This could, for example, happen if an engineer wants to analyze whether a policy he has learned in another tool has the desired properties and what the impact of different learning parameter settings are, so he wants to do learning pipeline assessment. In our case, this is the goal probability. To check how good the policy is, modes should deliver results about regions of the map where the policy reaches the goal with a high probability and which regions are dangerous. Let's have a look at these heat maps, which show the crash probabilities for all states. Green areas have a crash probability lower than 10% and wet ones higher than 75%. We see that the ring map is the most difficult one, especially close to its start line. This is because the track is narrow and the way to the goal is long. But also in the other maps, we see that states closer to the goal have a lower crash probability. The next use case shows the quality assurance versatility afforded by DSMC through an analysis quite different from the previous one. We did a stress test with our learned policies. The policies were trained in a setting with 20% noise to see how robust they are against unforeseen perturbances. We executed policies in a setting with 50% noise. In the parts close to the goal, it works well, but especially on this line at the beginning, the performance drops a lot. For comparison, we also analyzed the goal probabilities, which can be achieved in the 50% noise setting with an optimal scheduler to see if the deficiencies are due to the neural network or unavoidable given the high amount of noise. Finally, we are able to show that our deep statistical model checking approach can help to get insights about the learning performance, which is not visible in the training rewards. Here, we see the performance after 70,000 and 90,000 training episodes. When checking the reward curve extracted from training, the latter has a slightly better reward, and we would expect that the policy which has been trained longer is better. This is only the case for some parts of the picture, but not for this black area here. The additional training partially led to a catastrophic forgetting. The policy decided to stay at a position on the track without continuing to drive because staying where you are still gives a better reward than crashing. This phenomenon and the areas where it happens are not visible when looking at the training results, the reward curve only. Until now, we only saw results for policies trained on starting points anywhere on the map, which is the easiest setting. A big difference can be observed when having a look at the plots for ring map. On the left, we started on the start line only, on the right anywhere on the map. What catches the eye is that the lower part of the circle is much more preferred and the performance is much better there. The reason for this observation is that the first successful random routes reaching the goal led through the lower part. From this point on, the reinforcement learning process has a strong bias to that route, so preventing any further exploration of the top route. For random start, this is not the case because all start positions are explored, which introduces less bias. At the end, we remember the picture from the beginning and want to know whether DSMC is really a lightweight approach. Therefore, we investigate how long the policy analysis with the deep statistical model checking approach takes. We compare the effort for analyzing our neural network policies to that required for analyzing a conventional handmade policy that we incorporated into our Journey models. As the heat maps show, the latter effort is higher. This is due to a tendency to more risky behavior in the handmade policy, resulting in higher variance. While this is just a single comparison, it certainly indicates that high variance is not necessarily a problem specific to neural network policies. The runtime overhead for neural network calls is manageable in practice, at least for moderate-sized neural networks. To summarize, Deep statistical model checking uses statistical model checking as a lightweight approach to check the behavior of neural networks. Using the technical setup in modes, we were able to visualize deficiencies of neural network policies which are not obvious from looking at the learning curves. DSMC is a generic and scalable basis for analyzing learned policies, and we provide a formal and technological framework for precise and scalable problem analysis. In addition, the setup is very open to extensions and other problem structures because it is based on Jani models, which are supported by many other model checkers. Furthermore, we focused on an abstract fragment of autonomous driving, which can be refined and extended in the future, e.g. by finite discretizations, different surface conditions, moving obstacles, traffic participants, sensors, and so on. With deep statistical model checking, our goal is to foster scientific understanding of neural network efficiency.